In the last video, we introduced the law of conservation of momentum, a universal law that is particularly useful in describing collisions. In this video, we will explore a class of collisions called inelastic collisions. These are collisions that are solved using conservation of momentum without needing anything else. In a later video, we will explore elastic collisions, which require conservation of energy in addition to conservation of momentum. We'll start with a simple but unusual example: conservation of momentum when an object gains mass. For instance, this rail car gains mass as it is filled up with grain. Consider this puzzle. A 200 kilogram rail car initially travels at 0.5 meters per second rightwards. A hopper pours 500 kilograms of grain into the rail car. What is the final velocity of the rail car? In this question, we have a rail car which is moving along the ground. It has a mass of 200 kilograms. It's initially moving at 0.5 meters per second. It passes under a hopper. I'm going to call this photo 1 before any material starts landing inside the rail car. Later on, the rail car gets filled with 500 kilograms worth of material. So now its total mass is 200 plus 500 is 700 kilograms. Something like that. We do not know what its final velocity is yet. That is what we would need to solve for. And this would be photo 2. This situation can be solved using conservation of momentum. The total momentum before the material was dumped into the rail car must be equal to the total momentum after the material was dumped into the rail car. There is only one object here. So we could say that the total momentum of the rail car in photo 1 must be equal to the momentum of the rail car in photo 2. Momentum, in turn, is equal to mass times velocity. So the mass of the rail car in photo 1 times the velocity of the rail car in photo 1 must be equal to the mass of the rail car in photo 2 times the velocity of the rail car in photo 2. Now, let's substitute everything that we know. The mass of the rail car is 200 kilograms. The velocity of the rail car is 0.5, but you'll notice that I didn't follow one of my own rules, right? I didn't set the axes. I'm going to set the origin to be the back wheel of the rail car. I will set rightwards as positive. Now, that being the case, I can now say that the initial velocity was 0.5 I hat meters per second. And that's equal to the final mass of the rail car is 200 plus 500 equals 700 kilograms, multiplied by the velocity of the rail car in photo 2. 200 times 0.5 is going to give us an initial momentum of 100 I hat kilogram meters per second, which must be equal to 700 kilograms multiplied by the velocity of the rail car in photo 2. So the last step is just to divide both sides by 700. That gives us the velocity of the rail car in photo 2 is equal to 100 divided by 700, which is 0.143.
and this would be measured in meters per second. So this then is the final velocity of the rail car after this material was dumped into it.
A more common example is one where one object collides and sticks to another. An example is this train car at left colliding with the train car at right. Consider this puzzle. A 3,000 kilogram train car initially moves at 4 meters per second rightward. It collides with a 5,000 kilogram train car that is initially at rest. The two cars stick together as they continue moving. What is the final velocity of the pair?
In this question, we were told that a 3,000 kilogram train car looks something like this. Is moving at 4 meters per second rightward, and it's going to collide with a 5,000 kilogram train car, which is initially standing still. Before the collision, let's say that we took our first photo. And after the collision, we shall take our second photo. So in this case, we have a 3,000 kilogram object and the 5,000 kilogram object, which have now been hooked together using the linchpin and which are now moving together to the right. This is going to be photo 2. The point at which the linchpin engages, the point at which they actually make the connection, I'm going to call that my origin, and I am going to set rightwards as being positive. So I only really need to draw the axes on the latter photo, but just to be on the safe side, I'm going to draw where they would be roughly on the former photo. So there's my origin. This is where the back wheel of the 3,000 will be when it collides with the 5,000. Now that we have all of this information, let us proceed with applying conservation of energy, conservation of momentum to solve for the total velocity or the final velocity that this collection, this pair of rail cars is going to experience. So, the total momentum in photo 1 must equal the total momentum in photo 2. The total momentum in photo 1 is this time coming from two different bodies. It would be the momentum of the 3,000 plus the momentum of the 5,000, and that must be equal to the momentum of the 3,000 after the collision plus the momentum of the 5,000 after the collision. Let us expand these out using the definition of momentum. Momentum is equal to mass times velocity. So that's mass of the 3,000 times velocity of the 3,000 in photo 1 plus mass of the 5,000. And to be clear, let me say mass of the 3,000 in photo 1, mass of the 5,000 in photo 1 as well, times the velocity of the 5,000 in photo 1 is all equal to mass of the 3,000 in photo 2 times velocity of the 3,000 in photo 2 plus mass of the 5,000 in photo 2 times velocity of the 5,000 in photo 2. This that we have over here now breaks down momentum into its simplest possible terms, just the masses and the velocities. So now, let's go ahead and let us plug in all the information we know. The initial mass of the 3,000 is obviously 3,000. its initial velocity is 4 in the positive x direction. So that would be 4 I hat. Plus, the mass of the 5,000 is, of course, 5,000, times the velocity, which is initially it's at rest, so that's 0. All of which is equal to mass of the 3,000 after the collision, times the velocity of the 3,000 after, we don't know what that is. Plus mass of the 5,000 after, well, that has not changed from what it was before, times the velocity of the 5,000 after. Now, there are a couple of simplifications that I can make here. Let's start by simplifying this entire left side. 3,000 times 4 gives me 12,000, so this now becomes 12,000 I hat plus 5,000 times 0 is, of course, 0, is all equal to 3,000 times the velocity of the 3,000 object at photo 2 plus 5,000 times the velocity of the 5,000 object at photo 2. So that's our first simplification. Obviously, this left side will just become 12,000 I hat. But there's another simplification. These two objects are moving together. That means they have the same velocity. In photo 2, the 3,000 kilogram track, or the 3,000 kilogram rail car, and the 5,000 kilogram rail car have the same velocity. That means that this velocity over here and this velocity over here are the same thing. And whenever that is the case, you can factor it out of this expression and just call it V final and put it out front. So that would look something like this. The left side now becomes 12,000 I hat is equal to, these two I will call V final, and I will factor them out. The coefficients are going to remain within parentheses. So I now have 3,000 plus 5,000. Really all I've done is a sort of reverse FOIL. I have pulled these two terms out and called them V final, and these two coefficients now go within the parentheses. Simplifying further, we get 12,000 I hat equals 3,000 plus 5,000 is 8,000 times V final. And now we just divide both sides by 8,000 to get V final is equal to 1.5 I hat meters per second. So this is now the final velocity of the pair of train cars after the collision occurs. Now let's look through how we solved this. We started by listing out all of our information in the two photos and setting origin and axes. We used conservation of momentum, that is the total momentum before must equal the total momentum after. We expanded out so that we talk about the momentum of each individual object, and then we expand that out to provide the definition of momentum, mass times velocity, for each one of these. When we start substituting things in, we end up with basically a numerical answer on the left side and an answer which has only one variable on the right side since the two velocities are the same. So we were able to factor this out and then we were able to solve. Now be careful that that factoring out procedure can only work if these two velocities are the same. In the next video, and in fact even later in this video, we will see examples where the two velocities are different, so this factoring trick does not work.
In the previous example, one of the colliding objects was initially at rest. Another possibility is that the two colliding bodies are both initially in motion, like these two figure skaters. Consider this puzzle. A 50 kilogram figure skater travels at 3 meters per second rightward. She is lifted by a 70 kilogram skater who is also traveling rightward. If their final velocity is 2.5 meters per second, what was the initial velocity of the second skater?
In this question, we have a skater and a second skater. We will distinguish them by calling them the skater on the left and the skater on the right. Initially, these two skaters are both in motion. The skater on the left has a velocity of 3 meters per second, and the skater on the right has an unknown velocity. The skater on the left has a mass of 50 kilograms. The skater on the right has a mass of 70 kilograms. So this is the scenario that we have when photo 1 is taken. Now later on, we are going to take photo 2, and that'll be at the point right after the right side skater has lifted the left side skater. So there's our 50 kilogram skater, there's our 70 kilogram skater, and we know that they are moving away at a final velocity of 2.5 meters per second. So this is photo 2. This is all of the information that we have been given. We've been asked to find out what the initial velocity of the 70 kilogram skater was. So now let's put in our origin and axes. Here's our origin. I will set it at the point of the collision, which is what we usually do. I will set x as being rightwards. And although it's not necessary to put it in photo 1, I'll also put it over here just for the sake of consistency and also to show, relatively speaking, where the collision would have occurred. It would have been about here. Now, we are ready to apply conservation of momentum. The total momentum before the collision always equals the total momentum after the collision. So let's expand this out. The momentum of the 50 kilogram skater plus the momentum of the 70 kilogram skater before the collision, let's call this 51 and 71, is equal to momentum of the 50 kilogram skater in photo 2 plus momentum of the 70 kilogram skater in photo 2. Let's expand this still further. The momentum of the 50 kilogram skater in photo 1 is mass of the 50 kilogram skater in photo 1 times velocity of the 50 kilogram skater in photo 1 plus momentum of the 70 kilogram skater in photo 1 would be mass of 70, velocity of 70, all of which is equal to mass of the 50 kilogram skater in photo 2 times velocity of the 50 kilogram skater in photo 2 plus mass of the 70 kilogram skater in photo 2 times velocity of the 70 kilogram skater in photo 2. Now that we have expanded all this out, let's start plugging in the information that we know. The mass of the 50 kilogram skater in both photos is of course 50 kilograms. Her initial velocity was 3 meters per second rightwards. That would be 3I hat. Plus mass of the 70 kilogram skater, that's 70, plus their velocity, that is initially unknown. All of which is equal to mass of the 50 in photo 2 would still be 50. Velocity of the 50, now these two characters are moving together, so their velocity is going to be the same. It's 2.5 meters per second, and that too rightwards. So 2.5 I hat plus mass of 70 times velocity of 70, which is, since they're moving together, again, 2.5 I hat. Now let's start simplifying all of this. 50 times 3 is 150 I hat, plus this term we cannot simplify any further. We could just write it as 70 V, 70 in photo 1, is all equal to 50 times 2.5 I hat. That's going to give us 125 I hat, plus 70 times 2.5 I hat. is going to give us 175 I hat. Simplify still further. 150 I hat plus 70 times V 70 is equal to 125 plus 175 is equal to 300 I hat. So, moving or subtracting 150 I hat from both sides, we get 70 velocity of the 70 kilogram skater in photo 1 is equal to 150 I hat, and dividing both sides by 70 at long last is going to give us 2.14. So the velocity of the 70 kilogram skater in photo 1 was 2.14 I hat meters per second. Now let's think for a moment about what this result means. If the right-hand skater, if the 70 kilogram skater had been moving faster than 3 meters per second, then they would have moved away before they could have possibly caught the 50 kilogram skater. So clearly the right-hand skater had to be moving more slowly. Now, we notice here that this velocity is lower than the final velocity. After the collision occurs, the slower skater picked up speed and the faster skater went down in speed. The faster skater went from 3 down to only 2.5, but the slower skater went from 2.14 up to 2.5. This is fairly typical in inelastic collisions. Generally, the slower object speeds up and the faster object slows down, but the exact extent of speed up or slow down is going to depend on what the relative masses of these two objects are.
Since momentum is a vector, the direction of motion matters, and the final velocity will be different if the directions of motion are different. Consider this question. A 2 kilogram object travels at 5 meters per second rightward. It collides with a 4 kilogram object moving at 3 meters per second leftward. The two objects stick. What is their final velocity?
In this question, we have a 2 kilogram object, which is moving rightwards, and a 4 kilogram object that is moving leftwards. The 2 kilogram object moves at an initial velocity of 5 meters per second, and the 4 kilogram object at an initial velocity of 3 meters per second. But since it's moving leftwards, I'm going to call this -3, and I'm going to bring the point home by drawing the axes at the point of collision, with the x-axis being positive. So this over here is photo 1. Photo 1 is the picture of these two blocks before the collision takes place. What about photo 2? Photo 2 occurs after these two boxes collide and stick. So here's the 2 kilogram box, here's the 4 kilogram box. Now, we think that these two are going to be moving, but we don't yet know in which direction. So I'm just going to label this as photo 2, and I'm going to maintain my axes. Again, the axes are generally more useful on photo 2 rather than photo 1 after the collision occurs rather than before, but as long as they're present and as long as they're unambiguous and as long as they contain all the information that's needed for the puzzle, it's not really such a big deal which of these pictures they appear on. Just make sure that they appear. Personally, I prefer them to appear on photo 2. Now, let us, now that we have all of this information, let us find out what this final velocity is going to be by applying conservation of momentum. The total momentum in photo 1 equals the total momentum in photo 2. So, how do we find the total momentum in photo 1? The total momentum is going to be the momentum of the 2 kilogram object plus the momentum of the 4 kilogram object. And all of that's equal to the momentum of the 2 kilogram object after plus the momentum of the 4 kilogram object after. I realize that the subscripts can be a little bit confusing. Here, when I say P2, I mean the total momentum in photo 2. Here, where I say P2, I mean the momentum specifically of the 2 kilogram object. So if you see the sigma sign in front, that means that I'm talking about everything that's happening in photo 2. If you see just P2, I'm talking about the momentum of the 2 kilogram object. Now, let us expand this out still further. The mass of the 2 kilogram object times the initial velocity of the 2 kilogram object. So if we want, we can sort of symbolize it like this. The momentum of the 2 kilogram object in photo 1 plus the momentum of the 4 kilogram object in photo 1, momentum of the 2 kilogram object in photo 2, momentum of the 4 kilogram object in photo 2. So now it's unambiguous that we're talking about the momentum of the 2 kilogram object in photo 2. Anyway, the mass of the 2 kilogram object in photo 1 times the velocity of the 2 kilogram object in photo 1 plus the mass of the 4 kilogram object in photo 1 times the velocity of the 4 kilogram object in photo 1 is all equal to mass of the 2 kilogram in photo 2 times velocity of the 2 kilogram in photo 2 plus mass of the 4 kilogram in photo 2 times velocity of the 4 kilogram in photo 2. Now, let's plug in all of the information that we know. The mass of the 2 kilogram is, of course, 2, and that does not change anywhere in this question. Initial velocity, 5 I hat, because it's moving in the positive x direction, plus mass of the 4 kilogram, 4, times its initial velocity, that's negative 3 I hat, is all equal to mass of the 2 kilogram, 2, times velocity of the 2 kilogram after, we do not know what that is yet, plus mass of the 4 kilogram, 4, times velocity of the 4 kilogram, we don't know what that is either. Let's simplify this left side. This turns into 10 I hat plus 4 times negative 3 is negative 12 I hat is all equal to the velocity of the 2 kilogram and the velocity of the 4 kilogram are going to be the same. And whenever that happens, you are allowed to factor out that common velocity. So it looks something like this. V final, 2 plus 4. Now let's keep going. 10i plus negative 12i will give us negative 2i, and that's going to be equal to the final velocity times 6. So the last step is to divide both sides by 6, and we get the final velocity equals negative 2 over 6, which is equal to negative 1/3 I hat meters per second. So this is the final velocity where we have two objects that collided and stuck, but they were initially moving in opposite directions. It just so happens that the 4 kilogram object, by virtue of its velocity, of its mass really, had slightly more momentum than the lighter object that was moving faster. So overall, this object is moving in the negative direction. It's going to move leftward. And the process is very similar to what we saw before. We start off by drawing our pictures, setting photo 1, photo 2, drawing our axes, and then applying conservation of momentum. Expand the momentum out to each one of the objects before and each one of the objects after. Then use the definition of momentum to expand further. Substitute for what you know. When you have two velocities that are the same, you can factor it out and just call it v final. And then, with some further simplifications, you get the final velocity of these two blocks.
So far, we've seen cases of objects colliding and sticking. But there's another possibility that is related to inelastic collisions: an explosion. An explosion is less exciting than it sounds. In an inelastic collision, two objects collide and generally stick. In an explosion, two objects are initially stuck together and then break apart. An explosion is an inelastic collision in reverse. Consider this example. An 80-kilogram man throws a ball leftward at 6 meters per second. He starts moving rightward at 1.5 meters per second. What is the mass of the ball?
In this question, we were told that a man was standing on a skateboard and he holds a ball. Initially, the two of them are not moving. So this is photo 1. However, the man then throws the ball and correspondingly starts moving backwards. We were told that the man throws the ball at 6 meters per second and starts moving backwards at 1.5 meters per second, and that the mass of the man is 80 kilograms. So this now is photo 2. Let us set our origin and axes like so. Now, because we set the positive x-axis to be rightwards, that means that the throw of the ball is leftwards, which is the negative direction, so correctly I should say -6. And what we were looking for was the mass of the ball. Let's go ahead and let us solve this using conservation of momentum. The total momentum before the explosion took place equals the total momentum after the explosion took place. Now, the total momentum in photo 1 corresponds to the mass of the ball, let's call that P sub B in photo 1, plus the mass of the man, let's call that P sub M in photo 1. And that's equal to momentum of the ball in photo 2 plus momentum of the man in photo 2. Expand it out still further. Mass of the ball in photo 1 times velocity of the ball in photo 1 plus mass of the man in photo 1 times velocity of the man in photo 1 is equal to mass of the ball in photo 2 times velocity of the ball in photo 2 plus mass of the man in photo 2 times velocity of the man in photo 2. Now that this is expanded, we can plug in all the information that we know. The mass of the ball in photo 1 is unknown, but its initial velocity is 0 because it's standing perfectly still. The mass of the man was the 80 kilograms, and I could add that information here as well, times the initial velocity of the man, but that was also 0. And that's equal to the mass of the ball in photo 2, which is going to be the same as what it was in photo 1, but we still don't know what it is, times the velocity of the ball in photo 2. The ball is moving at 6 meters per second leftwards, or -6 I hat meters per second, plus mass of the man in photo 2, still 80, times velocity of the man in photo 2, which is 1.5 I hat. So this entire left side is going to work out to 0 plus 0, And that's all equal to -6 mass of the ball multiplied by I hat, mass of the ball in photo 2 times I hat, plus 80 times 1.5 gives us 120 I hat. Now, let's move this this negative term to the opposite side. The entire left side works out to 0, so I'm going to add 6 mass of the ball at photo 2 times I hat to both sides. That gives us 6 mass of the ball at photo 2 I hat is equal to 120 I hat. Now I just need to divide both sides by 6 and I hat, if you're so inclined, and we would end up with mass of the ball in photo 2 is equal to 20 kilograms. And this, of course, must be equal to mass of the ball in photo 1. So in this case, we used conservation of momentum to solve for when a mass rather than a velocity was unknown. We started it off in much the same way. We draw our pictures, we draw our photos, and we draw our axes. Now, one thing which made this a little different was that this was an explosion question rather than an inelastic collision. So that means that the two objects started together and then flew apart, unlike the puzzles that we have seen so far. For some reason, by the way, explosions are my favorite type of question. I know I said they're less exciting than they sound, but I still like doing them. We then went about solving the actual math in much the same way as we have done before. So we started with conservation of momentum. We created momentum terms for each object in the story. We expanded these out to include the definition of momentum. We substituted in all of the known information, and then we simplified to find the mass of the ball in photo 2, which also happens to equal the mass of the ball in photo 1.
Let's look at that explosion in slightly greater detail. The total momentum of the person and the ball before the explosion was 0. So the total momentum after the explosion must also be 0. That means the leftward momentum of the ball and the rightward momentum of the person must exactly cancel out. The momenta must be equal and opposite. Now, let's keep thinking. The ball's initial momentum was 0, but it gained a leftward momentum. Its momentum changed. Or, to put it another way, the ball felt a leftward impulse. Meanwhile, the person's initial momentum was 0, but he gained a rightward momentum. Or, to put it another way, he felt a rightward impulse. So not only are the momenta equal and opposite, the impulses are equal and opposite. But impulse is also defined as force multiplied by time. And since the time of contact between the person and the ball is the same for both of them, that means the forces must have been equal and opposite as well. To summarize, because of conservation of momentum, the final momenta were equal and opposite. So the impulses were equal and opposite, so the forces were equal and opposite. Sound familiar? That's Newton's third law. Conservation of momentum explains why Newton's third law is true. There is a deep connection between our familiar concept of forces and the conservation laws that all motion must abide by. In this video, we used conservation of momentum to analyze one-dimensional inelastic collisions and explosions. In the next video, we will expand our analysis to collisions in 2 dimensions.